Right, hello, my name is Andrea Lynn. I'm a grad student at Penn State. And I'm here today to talk to you about the NEID Solar Telescope, specifically science and operations. So I'm a bit more on the hardware side of this solar science talk, but I mean, it's important to understand, what collects our data, where does our data come from, right? And so that's what I'm here to talk about today. So this circled in red here, this is the NEID Solar Telescope itself. It's this tiny little solar tracker that sits on the edge of the wind building, and it's routed through all the way to the NEID calibration room, and then to the port and to the spectrograph itself. And so, looking at this, the telescope part in more detail, we have this tiny little 3-inch telescope, which is basically a single lens that feeds sunlight into an integrating sphere. And this integrating sphere is critical for creating disk-integrated observations to observe the sun as if it were an exoplanet host star, where we have no spatial information. This is mounted on this commercial solar tracker that we bought off the shelf. This has an active tracking loop that keeps it centered on the sun with a quadrant sensor. And finally, we have this thing called a pure heliometer. This is a common instrument in photovoltaic science that we basically use as a bolometer cloud sensor. It captures all the light from about 200 nanometers to 2000 in about a 5-degree field of view. So, if a cloud comes in front of the sun, we'll see a corresponding drop in flux. And one of the reasons we want to include this, so this is information that's also captured by the NEID exposure meter, but we wanted this to be an independent check of the exposure meter during instrument commissioning. And so a lot of our design decisions for the solar telescope are geared not only towards, observing the sun, but also seeing what we can find out about instrument systematics. And so here I show the light path of the NEID solar telescope. So obviously we have to have a separate, fiber run instead of from the 3.5 meter wind telescope that NEID sits on. But these both go up to, the majority of the light path is the same inside the NEID port adapter. And then these are injected into the spectrograph science fiber the same way. And from there, they travel down the same fiber into this exact same optics. And so that allows us to tease out systematics that we see in from the port adapter through to the spectrograph. And so the way that we actually observe with the solar telescope on NEID, we have an automated script that swaps NEID between the day and night observing configurations. This is all automated. It's worked really well for us so far. Pretty much no human intervention required. We take 6 hours of data per day between the morning and evening cal sequences. We take data straight through our daily liquid nitrogen fill. And the bottom plot here is showing that before we do the drift correction, we can actually see this disturbance from the LM2 fill in our solar RVs. And obviously this is all taken out by the pipeline to get final RVs. So you only see them in preliminary stages. And our location at Kip Peak means that we have a very large time baseline overlap for solar data with Express and also HARPS and NIRPS in the south, and also soon KPF. So this will allow us to compare multiple solar data sets together. We take a fast fixed cadence with 55-second exposures plus 27-second CCD readout. These are at very high SNR of about 400 to 500, depending on time of day and time of year. And so our fast cadence actually allows us to resolve the P modes in the solar RVs. This is a plot from my paper last year showing that with, I think this used about 6 months of NEID solar data, that we recover pretty much exactly the Bison solar P modes and their aliases. And so the data so far, before anyone panics, I will explain the bottom plot. So the data so far over 2.5 years, we have about 136,000 solar spectra total. So we started with when NEID started shared risk science in December 2020. There's unfortunately a break from June 2022 to November due to the Contreras fire on Kitt Peak. And so this is, at the bottom, this is all the data, every single solar spectra that I can pull from the NEID archive. So this is completely unfiltered. This is not cut by SNR. There is flagged data in here that we'll explain later. So if we do an SNR cut, then we see a lot of the anomalous points drop out. They're anomalous because they had very low signal to noise. But we still see these two kind of major disruption events, if you will. And so, obviously we wanted to figure out the cause of this at the time. And I will actually get to what caused these in a bit. But first, I want to show you that if we take out those two large events, as well as a couple more days, where the wavelength solution fell back to a less precise master, or et cetera, that over this 2 years, our solar data reveals an RMS of about 1.9 meters per second on the sun. If we bin over 6 minutes to approximately bin down the P modes, 1.8, and if we go to daily bins, 1.6. So this is, this includes not only solar activity, but also NEID instrumental precision as well. And so we do also see an offset with the thermocycling of NEID that happened due to Contreras fire, and it's about a fairly consistent 6 or 7 meter offset there. And that's something that we can clearly see in the solar data. And I would just like to note that all our data is public on the NEID Solar RV archive. It's processed within 48 hours, generally, using the same pipeline as the NEID nighttime data. It's the exact same pipeline. And this is publicly accessible with no proprietary period at all. And so moving on to some of the challenges that we've had to deal with adding this onto an EPRV instrument. One is, of course, the weather. Kitt Peak is not necessarily the friendliest place for outdoors instruments, but this was something that we took into account in our design phase, and the tracker and the telescope on it have survived quite well so far. And so now getting back to those two disruption events that I was talking about. So we did find that this was actually a mechanical problem with the solar telescope, solar feed itself. So we have this large cable bundle on the back of it, which feeds, the optical fiber as well as a bunch of communications cables. And that has unfortunately come loose twice. And this is about 10 or 15 pounds of cable, and it either torques the optics assembly, so it's actually shifting where the telescope is pointing, or it's just pulling on the alt drive of the tracker and causing the pointing to shift in that fashion. And so this is the cause of those two large, RV excursions that we see. Unfortunately, this is uncalibratable in the sense that it's not something that we can take out just by comparing it with, a wavelength solution, because this is not part of the, let me rephrase that. This is due to the solar tracker itself. It's not a larger NEID instrumental problem that we can easily deal with. So here I'm showing basically, we see the RVs slowly start to creep away from where they are. And then, once we reattach that cable bundle onto the tracker, thankfully it fixes itself fine. And this is the exact same thing that happened a couple months ago. And I would like to note that we're working on basically flagging these in the data quality bit fields. So in the future, if you're using this data, you will know that there was a tracker problem, et cetera. And so I would like to quickly highlight as well a couple of the current solar projects that people are working on. We've already heard from Jared and other people that people are using this data to great effect. But I wanted to highlight a couple more projects that people at Penn State are working on. So Eric Ford and colleagues at Penn State are developing a research pipeline for the NEID solar data that it goes beyond the standard NEID DRP, and we're using curated line lists and trying to apply activity mitigation techniques, et cetera. And from that, we can see that the NEID order by order RVs are individually precise. So, each order has a daily or within day RMS of, a meter and a half per second. These are also provided by the DRP, but this is with the Penn State research pipeline slightly improved. Another project that people are working on is looking at the structure of stellar noise. So if we look at the RMS as we bin more observations together, we see that it decreases more slowly than 1/√n, which is the blue line there. And this is due to longer term solar noise like oscillations and granulations. And so Zhao Guo and Jacob Loon worked on developing physically motivated GP models for these types of solar activity. And we're working on calibrating this model using the solar observations. All right, so here are my conclusions. I will leave this here and take questions. Thank you.
All right, do we have any questions? Okay, Save's got one here and then we've got one more over there.
Thanks a lot. I had a question on HARPS and HARPS nodes, what we see daily. We really start to observe very soon the sun at very high MS. We see some differential extinction effect. I was not able to see here in your data. So do you see the effect as well or no?
So we think we see it on a day-to-day basis. What we see actually is a slope in the solar RVs. We're not sure if it can be entirely attributed to differential extinction. That's not something that the default pipeline deals with, but it's something that people are working on. Couple meters per second, 1 or 2, I think.
Okay, and we'll have one last question as Joe gets set up here. So we're going to take your slides away from you, sorry, but we'll let you answer this one.
Okay, well, that first question was exactly what I was going to ask. So since it's been asked, I'll switch to a suggestion. You could observe to very high air mass, and then you would see the differential extinction, and you'd calibrate it across for.
Yes, the problem with that is that we're limited on either end by the morning and evening NEID cal sequence. So we only observe above air mass roughly of 2.
Oh, well, maybe you could change the cal sequence.
Oh no,
Okay.
Chad would be unhappy.
Okay.
Chad would be very unhappy.
Okay, I don't want to be too radical here.
We don't see the slides. All right, let's thank our speaker again.